Welcome to my presentation. Let's start with two main issues in analog design automation. One aspect is that circuit simulation is extremely expensive. If you have real-life problems, one single simulation can easily take several minutes. For instance, if we assume it would take 5 minutes per simulation, and if we would need something like 1,000 simulations, and assuming you can't parallelize them, and you cannot parallelize all of them, you would wait 80 hours till you have your result. So that's a very long time. The next issue is that the design knowledge that is to be incorporated in the design is ubiquitous. It comes from the physics, from the devices, it comes from the physics of the process technology, and even worse, it's implicit. It's in the brain of the designer. So you have constraints like symmetry matching, the operating regions of transistors. For the placement, you have to think about the alignment, about common centroid, interdigitation, whatever. So the main two questions that any EDA tool for analog design has to answer is how many simulations does it need? The overall number of simulations that you need for the whole process, including the modeling part. That's a crucial question if it's realistic what this tool can do in practice. And the next important question is how comprehensively and fast are all these implicit constraints set up? Commercial frameworks very often provide, graphical user interfaces and input tools to do that, but you have to code it all by yourself. When we look at EDA tools for analog, one can see three main types of focus that they are following. One approach is the statistical focus. This is basically what you nowadays call machine learning, which in the end is about statistical methods. The nice thing is the learning in these methods is inherent in the algorithm. That's a nice thing. You don't have to worry about where you get the knowledge, but the problem is the learned knowledge stays hidden. You kind of move it from the brain of the designer into the neural nets of your statistical method. And as this is somehow reproducing a kind of natural evolution, you end up with huge simulation costs. So this is very costly. Another type of focus would be what you could call the module focus. So you think about to get a silicon compiler, you get to the layout in the end in one step. It's very slow to implement a module generator. Once you have it, the execution is very fast. That's the nice thing. But it usually does not scale. It has a low reusability because very often a module generator is just implemented for just one circuit and you don't know how to do it for the next one, or you just copy or do everything anew. So what I would like to call a deterministic focus, this is something where you first capture your knowledge in a white box manner and put it in analog cell libraries, and such cell libraries are a little bit more complex than digital libraries, and they are more than just modules. And you have to think about an automatic setup of your design objectives and constraints as a part or out of these libraries. And your design approach should be something like a guided or bounded optimization way, or construction, or sometimes even enumeration. And when you do this, you usually end up with pretty low simulation cost. In the following, in the paper there are more of them, but in the following I would like to pick two examples for approaches which are more on the deterministic focus side. One on statistical design and one on something that I would like to call a functional building block library. So let's start with the first one, statistical design. So statistical design is about considering beyond the nominal behavior that your circuit is suffering from variation from the process, from the manufacturing process, from the operation with voltage and temperature variation, and from process-induced mismatch among different devices. You capture the quality of a design with regard to these variations by the so-called yield, and this is the percentage of circuits that satisfy given performance specifications. And it's actually obtained by determining the integral of your probability density distribution of the statistical variability of the parameters over a given acceptance region, which comes from specifying performance bounds. So here on the left side, you can see the Gaussian bell curve, right? This is the probability density function of a normal distribution, which you can assume as a basis. So if the real parameters are not normally distributed, you can transform them internally in your tool into normally distributed parameters. So here we have an example with two parameters. Let's assume, I don't know, this would be threshold voltage of one parameter, threshold of one transistor, threshold voltage of another transistor. The level contours of the normal PDF are determined by this quadratic form, where x as 0 is the mean value and c is the covariance matrix, which includes the standard deviations and the correlations. And the level contours of the PDF are ellipsoids around the mean value, the shape of which are determined by the covariance matrix. Now in this parameter space, right, this is the two statistical parameters. X as 1 is the threshold voltage of the one transistor, this one of the other one. When you pick one specification bound, right, so some value FB for one performance feature, and you should be below that. And then there is something like a line, well, a hyperplane here, if you have more than two parameters, which separates the parameter space into two halves, right? This is where the circuit is violating the performance spec value. The blue one here is the half space where it satisfies it. Now the yield is the integral of the probability density function over this acceptance region, right? The whole Gaussian bell curve is 100%, all of them, and this line here, or this hyperplane, cuts away from what I always like to call the Gaussian bell cake, right? It's a cake. You cut away from the cake, you cannot sell the whole cake. Now you want to maximize that yield, right? Now to determine the yield, you usually use as a statistical approach the Monte Carlo analysis. The problem is we are talking about rare event analysis tasks. So this kind of violation is not very probable because you have a robust design. This is what you want. So you need a lot of simulation and you have to care much about how to get this. And the number of simulations is incredibly large. So the question is, can we do better? So the question is, can we do something like a deterministic characterization of a rare event problem? The question is there one point to determine that kind of shift from good circuit to bad circuit? And you should please stop here when you watch the video and think a moment about, can you imagine if there is one point to determine that problem in such an example here? Of course, the answer is yes, there is. And now here comes, and this is a wonderful definition, so please keep it in mind. We are looking for the point of highest probability to violate the spec. So mathematically, it would be correct to talk about highest probability density, but easily, you know, it's more easy to think about point of highest probability to violate the spec. And it's this point here, right? If you think about that Gaussian bell curve here, the larger the radius of this level contour, the smaller the corresponding PDF value. So when you go in this space here, the values become smaller and smaller. So it's more and more improbable. Now, the radius with the smallest radius, the point with the smallest radius gives you the largest PDF, which is the most probable point. So you just look at one point, the most probable point to violate the spec. That's a deterministic characterization of the rare event problem. And it's a not simple, but it's a specific nonlinear optimization problem which can be solved. Once you have solved it, we have shown that when you use the radius beta W of that level contour to which the worst case point belongs, you can immediately look up the yield value in a statistical table, right? This is a one-dimensional thing. And now this is a standard normal distribution with mean value 0 and standard deviation 1, and then this integrating to beta w, you can take this beta w, the so-called worst case distance, in this wonderful practical thinking of beta w sigma. Is it a 1, 2, 3, 4, 5 sigma design? You also get a gradient for the optimization, and all this is implemented in the tool, which is sold by the company Munich. How do you see examples here? So here we have an example. It's an op-amp. We have 5 performance features. Excuse me. Now the initial design here, you see all the worst case distances, right? This is 1 sigma, 2 sigma, 3 sigma, 4 sigma robustness. And the yield value refers to the sigma easily, right? Worst case distance sigma means your nominal point is right on the border. So half of your circuits is good, half of the circuits is bad. This is 50%. We want to maximize all of them. And the nice thing is you look at them individually, so you can see here, oh my goodness, here the phase margin, that's a very low robustness. When you optimize the circuit, you end up here with the minimum worst case distance as 4 sigma. So you can say this is a 4 sigma design probably. And you cannot improve from here, because if you increase the phase margin, you decrease the slew rate, which means you have the optimal trade-off between stability and speed. That's what you could do here. Okay, so we start with a structural building block library. This is a library of basic current mirrors, a differential stage, and corresponding sizing constraints. So we have looked at all possible transistor pairs which have a relevance for the circuit design. And there are just these 8, right? I think from the bell number, it's, when you can connect 2 transistors, each with 3 pins, let's say basically 3 pins, you can think about, I don't know, it's 200 and something possible combinations, but only 8 of them make sense from the design point of view. Now, from such simple pairs, you build more complex groups, like pairs of pairs or combinations with transistors and so on. And first of all, there are very different types of current mirrors. And then we have written down the way how they are composed in a computer-oriented way, and we have written down all the sizing rules which you can get for, not all of them, but part of them, right? For a differential pair, you have 4 sizing constraints which you have to consider. A MOS transistor can be a voltage-controlled current source. There you have 6 sizing rules, and so on. Now, if you build up a circuit, for instance, if you have a wide swing cascade current mirror, which in the end consists of 4 of these VCCS, then you have 4 times these 6 sizing rules. So if you have a small circuit, you quickly end up with, I don't know, 200, 300 sizing constraints, and you don't want to put them up manually. So what we have done is we have created, mathematically, it's a subgraph isomorphism search, where you go through a flat netlist and you browse and find out where all these transistor pairs and groups are. You automatically set up these constraints. You feed whatever optimization tool you have for sizing, and this enables automatic sizing of a circuit to a reasonable result in practice, right? This is also included in tools by the company Munich. Now, you cannot only use that for sizing. We have used it for a placement approach, again with the deterministic approach, because when you write down the hierarchical composition of, for instance, such an op-amp, so you can say this circuit consists of several blocks, for instance, of a differential stage, which is this one here, this part. The differential stage consists of a differential pair, which is this one, and a cascade current mirror, which is the part down here. Then you have a wide swing cascade current mirror, which is the part over here. You have the 4 transistor current mirror, which is this part here, and so on. And then you have a hierarchy of the circuit. Now, what we did then is you can again automatically create not sizing rules, but the placement constraints out of this automatic netlist analysis, and you can automatically create a placement plan which goes bottom up according to this hierarchical decomposition. So you start at the bottom level, and here you do placement enumeration. of small transistor groups, which means you really write down all possible layouts of these small groups. Right here you can see a group has 2 or 3, here 4 transistors, and you write all these placements down. You code them in the B-star tree, and then we have found out that you can formulate then of a vertical and horizontal merging of these B-star trees bottom up. And this is going along this hierarchical placement plan. So you somehow have something like a guided, or no, you could say bounded enumeration, because it's bounded that you do not try everything on the top level, but you just go bottom up along these hierarchical compositions. And we have shown that when you go bottom up with this merging, you can show proof that it is always constraint compliant, right? You never violate a constraint that you have set up on a lower level. You just add more constraints on higher levels. And by the way, when you have the B-star tree, you can set up a horizontal and vertical constraint graph. From that, you can get the X and Y coordinates by an integer linear programming approach. Now, in the end, for the whole circuit, you end up with the shape function here for all possible aspect ratios of a circuit. Right here we have seen, here we show several examples. And for each of these possible placements here with the dots, you have the B-star tree, and then you can say, what is this now? How does it look like? The interesting thing is the whole thing takes a few seconds, maybe a minute, which means the user can look at the placements. And usually what the user does is he or she looks at the placement and sees, those 2 transistors, they don't really are where I want them. And then they find out, oh, we need another constraint. You add it, the constraint, restart, takes another seconds or minute, and you can look again and proceed to what you want here. So you can see we have done here from, we created white box knowledge. And in particular, we have a library bottom up. How is the circuit built up? And from that, we create the constraints, the objectives, and very specific design plans. In the meantime, the structural consideration of block libraries has been extended to a functional consideration. This is more complex, as functional block mapping to structural block mapping is a one-to-many or many-to-one mapping, right? So you cannot just find out in a given netlist, oh, this is the function of transconductance, here are load functions, this is the first stage, there are bias functions, but you can put it the other way around. So if you want to design an op-amp, for instance, let's say a single output op-amp, like blue marked here, it can be a symmetrical one, a 2-stage one, a 1-stage one, or maybe even more than that. But then if you decide for a 2-stage one, the first stage consists of these types, then you have a common mode feedback stage, you may have a second stage, which in turn depend on the implementation of stage bias and so on. So writing down this, again, white box knowledge, get it out of the brain, write it down in a computer-oriented way. And it has been able to write down also hierarchical equations, which can be combined between the hierarchies, get an initial sizing, and really formulate a quick structural synthesis approach. So the overall message is, let's do this as a kind of conclusion. What are don'ts and do's for analog EDA? Don't hide the analog design knowledge in a neural network, be it human or be it a machine one. And don't code the design of every analog circuit type from scratch, but try to capture the design knowledge of, well, the right building blocks. You have to find the building blocks which have a disseminator capacity to analog cell libraries that can be used throughout analog design. And then do tools to an automatic setup of the constraints and objectives within this library and netlist consideration. And do design tools which are using these guidelines, constraints for guided optimization, construction, which is less than optimization, or even bounded enumeration. Thank you very much.